notes, we're going to be talking about three-dimensional shapes. We're going to be taking two-dimensional shapes and turning them with different techniques to turn them into three-dimensional shapes. So this is called like a solid figure. So two different methods you're going to learn, actually three. Number one is the disk method. Talk about that. Then you have the washer method. Then you have solids with known cross sections. That's completely different than those first two. Then the AP standard for this one is just to be able to find volume of solids given a variety of methods. So depending on the problem, the application and whatnot, that's what it depends on. Then your homework problems at the bottom. So first of all, there's some definitions that we have to get down. The first one is a solid revolution. So in a region, that's when a region in a plane, so you're talking about a two-dimensional plane, okay, like on graph paper. And then you take that plane and you rotate it around an axis, creating a 3D figure. So that's a solid, all right? So that's talking about the disk method. We'll get into that a little bit, but you flip it around what's called an axis of revolution. So that's down here. So axis of revolution is a line the region is spun around. We'll do different. It's not always y equals 0, x equals 0. It can be whatever. It's just where it's spun. And then the disk is a product, the result of spinning a specific region around an axis, like if you look down here. Alright, so think two-dimensionally, you just have a line with a width, so it's a rectangle. Then when you take that rectangle and spin it, you have what's called a disk. It's like a quarter. Alright, think of that as like a quarter. So then, the volume of the disk, is this part right here. That's the volume of the disk. Now, we want to find the volume if we took every single little part. So if we had a bunch of rectangles lining this curve and then you flipped each single rectangle, it might look like something down here. Alright, creating a solid three-dimensional, but since you're having an infinite amount of rectangles, the sides are going to be smooth. That's where we come into the Riemann sums. And so then we go from a Riemann sum into an integral. So it starts here, the volume of a solid. This adds up all of those little areas of your disks. So the Riemann sum adds up all of those areas of your disks. But that's pretty limited, alright? Because you can only go from 1 to 2 to 3 to 4 to 5. But this, now we're saying this is as a limit problem. This is saying the limit as a change in x. So these disks are getting infinitely small because the distance from one to the next is 0. So infinitely small. Then this part right here, this Riemann sum, converts to what we have worked with and know as the integral. Alright, now the area of a disk, if we come back up here, is pi r squared. That capital R, that's just the radius. That's just the radius. So the area of a disk is just pi r squared times the width. Alright, but that width, it changes. That's where this down here, that's where this dx, change in x, okay, and then with this limit, the change in x is approaching 0. So, but we have to account for each change, and so that's where the dx comes from. And then on here, you notice these two are the same, except the second one has y's, because sometimes you flip it around your y-axis, or your rectangles are perpendicular to your y-axis. So you have those two. So it's pi times the integral of your radius squared times dx or dy, whatever function you're using. Let's try a problem. So again, try this on your own, then come back and see how you did. First thing we're going to do, finish this problem. You should write and the x-axis. Forgot to do that. Because you got to spin it around some axis, and so the axis of symmetry in this case is the x-axis, and you're doing it. If you graph it, you might have been able to figure this one out, but you're going to go from 0 to pi. right? And that's about the x-axis. So first of all, first thing I like to do is to start my integral. Before I start my integral is figure out what my radius is going to be. Okay. Now your radius is going to be defined by whatever function, because remember that radius, as it moves along from left to right, in this case, that radius is going to change heights. So it's going to be defined by your function. In this case, it's the square root of the sine of x. First thing we do is figure out what your radius is. Now, let's find the volume. Oh, not the volume, the area of one disk. So the area of the disk is going to be pi r, which is the sine of x squared. And so then that's just going to be the sine of x, so pi times the sine of x. That's the area. Now to get the volume, we're going to take those and just layer them like a bunch of Pringles chips. Just layer all of those disks together using the integral. And our limits, if you look up here, from 0 to pi. And this pi is a constant, so we're going to pull it out. That pi goes out there. And then pi r squared, and so our r squared is sine of x. So it's just going to be sine x times dx. And we can integrate from there because it just gives us a negative cosine, so it's going to be pi times a negative cosine of x. And then our limits are from 0 to pi. So then you'd have pi, when you plug negative, or when you plug pi in the negative cosine, you get 1. Minus a negative, that's plus a positive. When you plug 0 in there, you get 1. So you end up with 2 pi. That gives you the volume of that solid spun around the x-axis, defined by the square root of sine x. If you want to graph it, take a look at the graphs. Some of these other ones we're going to actually look at the graphs, like on this one. Let's just sketch a graph. So take a minute and sketch a graph really quick. You have 2 minus x squared. That means it's upside down, moved up 2, and it's a quadratic. So it's going to look something like this. It's 2 minus x squared. Revolving by that, and g of x is equal to 1. So let's draw that line. That is this line right here. G of x is equal to 1. Or y is equal to 1, whatever. And about the line, it says y is equal to 1. Oh, did I do that one right? Yeah. Okay, so g of x is equal to 1 and y is equal to 1. They're the same thing. So also, your axis of revolution right here. This is your axis of revolution. That's where you're going to spin this thing around. So really, I'm going to color in black here the solid piece that's going to be spun around. So it's going to be like a sphere with a hole in it when you spin it around. So just think about that for a minute until you can get a mental picture of this. I wish I was a better artist. Maybe one of you can come in with a great picture of this. But it's going to be a sphere with a hole in it, like a little bead. Okay, so first of all, find the points of intersection. We need to figure out what these points are here in order to set up our limit. So just set the equations equal to each other. 2 minus x squared, that's the purple one, and it meets the green line, which is just 1. So when you go through and solve, you get x is equal to positive and negative 1. So it crosses at 1 and negative 1 here. Not your x-axis, but it crosses the green line. So then that gives us our limits. Goes from negative 1 to 1. And then your radius Okay, now your radius, you're going to, in order to figure out, like if I were to draw one rectangle, so in this red line's a rectangle. The radius is defined by the height minus the lower, so it's the upper minus the lower. So it's going to be your upper function, which is your 2 minus x squared, minus your lower function, which is just y equals 1. Because with this rectangle, the distance between those 2 points is the top point minus the lower point. The top point is defined by 2 minus x squared, and the lower point is defined by negative 1. So then when we simplify this, this is going to be 1 minus x squared. Or let's rewrite it, negative x squared plus 1, doesn't matter. And when we get there, remember it's radius squared, because remember the area is pi r squared, so it's going to be pi times r, which is negative x squared plus 1 quantity squared. So we need a pi out in front of these. I started my integral too early. I should have come up with the area first. And then also we're going to square this. Pi r squared. There we go. Now we're all set and ready to go. So my bad. So set up the area function first and then integrate that. That'll lessen mistakes. When we integrate this, you can't use U substitution. It's not an inverse trig property or anything. You just straight up have to multiply it out. And when you multiply it out, you end up with x to the 4th minus 2x squared plus 1 times dx. Now we can integrate that, so it's going to be pi times, it's going to be x to the 5th over 5 minus 2x to the 3rd over 3 plus x. Now here's something that we could do to make this a lot easier. So this is an even function, right? It's an even function. Look, the area on the left and the area on the right of this function are the same. So instead of going from negative 1 to 1, we could go from 0 to 1 and then just multiply the whole thing by 2. It'll make it a lot easier, especially since we have those fractions in there. Now it's a negative 1, so I guess it doesn't matter, but anywhoosie, that's what I'm going to do because I can just forget about the bottom limit now. So then you would have 1 to the 5th over 5 minus 2 times 1 to the 3rd over 3 plus 1. And then when you simplify all of this, get common denominators of 15, then multiply the 2 pi in, you end up, go ahead and work it out yourself just for practice, but you end up with 16 pi over 15. And then that gives you the volume. So if this were an application problem, make sure you would label this. So it'd be units cubed. Okay. And remember, even and odd functions, if you know that it's an even function, then especially if you can graph it and see that it is, then by all means split it in half and multiply by 2. It makes it a lot faster. So the washer method we actually just did. I did that one a little too soon, but that's okay. The washer method is, in a sense, just taking the middle part out. Just like on that last one, you had a hole in the middle. Alright? And so you ended up taking that middle part out of there. So your upper function is f of x, your lower function is g of x. This is just like when you were finding the area of a like a two-dimensional region. If it was between two curves, you took your upper function minus your lower function and integrated between wherever on the x-axis. All right. So that's all this is. Let's take a look at this one. First thing we want to do is try to sketch it. So if you haven't already, go ahead and try to sketch it. But we have square root of x. Then we have x squared. And now what we want to do is we revolve it around the x-axis, and we're going to revolve what they have in common. Blue and purple make I don't know. In this case, they make red. Alright, so this red part is the part that's being spun, and it's being spun around the x-axis. So you're taking it and you're spinning it around here. Okay, so try to think about the shape. It's going to be a really odd shape. It'll be kind of like a very pointy. It's not going to sit on the bottom, but a very pointy cone with a, I don't know, you could put your nose in it or something. I don't know. Looks like the front of a spaceship or a bullet or something. Anyway, so that's the region that we're going to have. So again, this was the square root of x, and this was x squared. Now let's figure out one of those disks. Okay, if you figure out one of those disks, the area. Now one of those disks is going to, if we just put, it's spinning around the x-axis, so our rectangles are going to be perpendicular to the x-axis. So here's a rectangle. Alright, now imagine spinning that around and you would have a disk. And so if you think of it from the front, the disk would look something. Now obviously as it went in, it would get, you know, the middle would get narrower and narrower and narrower, but basically this is what you're doing, where this out is your capital R of x, and this inner radius is your little r of x. And the area is going to be pi times big R of x, and in this case your outer function there is square root of x, quantity squared, and then it's going to be minus your inner function, which is x squared, quantity squared. So pi times that. So it's your outer function squared minus your inner function squared. Now our integral is going to be a step further. It's going to be our area. So if I square this, you get x. X squared squared is x to the fourth. And then now you have to figure out your limits. So in order to figure out your limits, you would set them equal to each other. So you would set the square root of x equal to x squared, and when you do that, you get 1. So you're going from 0 to 1. Okay, so now we can go ahead and integrate. I'm just going to come down here. After you integrate, you're going to have pi times, you'd have x squared over 2 minus x to the fifth over 5, and that's from 0 to 1. So you'd have pi times 1/2 minus 1/5. And then when you simplify that, you'll end up with just 3 pi over 10. And again, oops, you might want to label it. It'd be cubic units. And then that would be the volume of that shape, the total volume of that three-dimensional solid. Okay, let's try one that's a little more involved here. So find the volume of the solid formed by revolving the region about region bounded by the graphs there, and then sketch the problem. So there's one other part to this that you have to know before you try this on your own. The part again that I left out is you're going about the y-axis. So you spin it about the y-axis. Spin it about the y. So first of all, let's set this up. You have x squared plus 1. Let's do this in green. So x squared plus 1 would be something like, let's say, That's actually not bad. I'm impressed. Bet you are too. Then your next one, y equals 0, is this line here. X equals 0 is this line here. That's not so straight. That's okay. And then running out of colors here. That yellow, blue, green, red. We'll just do red. And then yeah, x equals 1. So x equals 1. Y equals 0. But now since we're spinning it around our y-axis, let's come back here. Spinning it around our y-axis, what that means is, if I draw a rectangle, our rectangle is going to be perpendicular to our y-axis here. Alright? Now, when you spin this thing around your y-axis, if I just real quick, you're going to get a shape. So here's the squared function. Oops, let's just come down here. You're going to shape that looks kind of like this. So here's the problem. You're going to have to set up two integrals because some of your rectangles are going to have a height defined by this function and this function, and then some of them are going to have a height defined by this function and this function. So you're going to need two integrals for this baby. Alright? Now your first integral, let's do your first integral as this. No, we'll do the low one. Let me color this. So that's the area that you're going to find with your second integral. And then in green, this is the area that you're going to find with your first integral. Because they have two different heights as you move up and down your y-axis. Okay, and again, they're perpendicular. Your little Riemann rectangles are perpendicular to your y-axis there. Alright? Now, let's set up the first one. Your limits, in order to figure out what your limits are, well, in this case, it's just 0 to 1, because it's from here to that point there. And remember, it's going to be pi times r squared minus r squared. So your rightmost function minus your leftmost function, and your rightmost function is x equals 1, and your leftmost function, so that's 1 squared. Your leftmost function is x equals 0, so that's 0 squared. And this is with respect to y, so these are in terms of y. That's your first integral. Then your second integral is a little trickier. It's still going to be pi. Now, when it's with respect to y, what we have to do is we have to take these functions and solve for x. So if you take y is equal to x squared plus 1 and solve for x, you'll end up with, what is it, square root of y minus 1. Right? So then that's your green line right there. That's your green line. So then if you were to draw the heights of a rectangle in here, it would be from the red line to the green line. So when we set this up, it's going to be from the red line squared, which is 1, x equals 1 squared, minus the green line squared, which is the square root of y minus 1 times dy. And then your limits, okay, your limits are found where they intersect, and you're going from 1 in this case. If you find out where they intersect up here. The picture's a little off, but up here is y equals 2. So they're going to intersect, go from 1 to 2 on your y-axis. right? So these variables, these right here, what are these? Your limits. Okay, your limits have to be on your y-axis since this is with respect to y. So it's moving up and down your y-axis this time. Now, let's go ahead and integrate. Here, it's going to be pi times the integral of just 1 dy plus pi times the integral. This, if you simplify this, because you'd have 1 minus y minus 1, then that negative simplifies or goes in, and you'd end up with negative y plus 2 with respect to y. Now we can integrate. When you integrate this, you'd end up with 1y integrate this, you'd end up with negative y squared over 2 plus 2y. And that goes from 1 to 2. This isn't an even function, so you can't do what we did last time. And so this is just pi. Here you have to simplify. You're going to plug 2 in, so that'd be negative 4 over 2 plus 4 minus negative 1 over 2 plus 2. And then when you simplify all of that, you end up and then multiply, or this, sorry, when you simplify all of that, you would end up with 1/2 pi, so it'd be pi plus 1/2 pi, which gives you 3 pi over 2 or 1/2, either one. And that's units cubed. So then there's our answer there. And again, that's with respect to y-axis. So you're turning everything so that your rectangles now are perpendicular to your y-axis as opposed to your x-axis. Other than that, you would solve all the variables or all your equations for x, and then everything else is the same, just on the y-axis instead. Okay, let's try another one here. Oops, next one. Okay, so this is very similar to one we already did. Okay, it's very similar to the one we already did where you're taking a sphere and drilling a hole through it. It might be a little different, but you want to drill a hole through the center of a metal sphere. The sphere has a radius of 5 inches. The hole has a radius of 3 inches. What is the volume of the resulting metal ring? So I'm going to try to draw this. Don't laugh. Okay, that's our hole. And then our sphere, like that. And then out of here you have your x-axis, so that's your x-axis. And then your y-axis, the other side of your x-axis, and then your y-axis. So this kind of looks like an eyeball. Let me shade this in real quick. Yeah, I know, you're pretty amazed at this point. I know. Alright. So, it's kind of like an olive. Alright? We know that if this came the rest of the way down, it would be at 5. Alright, so now, first of all, let's figure out your little r. That's your inside radius. And then let's figure out your big R, that's your outside radius. Your little r, your inside radius, is defined by this line here, which is at 3 inches. So it has a radius of 3 inches. So it's about the line y equals 3. And then your big one is basically you have a circle. And the area of this circle is, let me bring it up here, the area of the circle is x squared plus y squared is equal to r squared. And in this case, your r is 5, so it's going to be 25. Now, your equation for your radius is going to be solved for y here, since we're spinning around the x-axis. When we solve it for y, you'd have 25 minus x squared. Then you'd have the square root of that. Such a big R. Okay, now we need to figure out our limits. It's not going to be from, negative 5 to 5. It's not going to be like that. So when we find our limits, you're going to set those two functions equal to each other. So you want to know where they cross. So you have 25 minus x squared. That square root is equal to 3. And when you solve, you'd have 9 is equal to 25. Let's take square each side. And then x is going to be positive and negative 4 because you have 16 once you bring that over. So then our limits, it actually crosses here at 4. That's the tricky part. Not the rest of it's not tricky, but that's what I found to be the trickiest of the whole thing. And then the area of this thing, so it's the upper function squared minus the lower function squared times pi. Then we're going to integrate that. So it's your upper function squared, which is your big R. And you notice when you square your big R, you would have 25 minus x squared minus your lower function squared, which is 9. Now again, I'm going to change my limits and then multiply it by 2 because I can tell that this is an even function. It's the same on the left side of y as it is on the right side. So then you would have 25, whoops, not 25, 16. So then you would have 16 minus x squared dx. And when you integrate that, you'd have 2 pi and 16x minus x to the third over 3. And that's from 0 to 4. And when you plug the 4 in there, you get 64 minus 64 over 3 times 2 pi. You end up with 256 pi all over 3. And that's cubic units. There we go. Okay, so then that would be your final answer for that one. Now that's it for those kind that we're going to be doing. You notice you probably noticed this. And another thing that you could probably do, you could try it. I'm guessing you could. You notice with this, since you're drawing it out of the middle, basically what you're doing is you're taking a cylinder out of a sphere. Does that make sense? So you can figure out the volume of the sphere and subtract the volume of the cylinder. You should get about exact the same thing. So you can try it. But we're in calculus now, so we're doing it the calculus method, spinning it around in arbitrary axis. So let's try the next one. But before we do this, we have to talk about the volume of solids and with known cross sections. So I'm going to fill them in so I can talk about them. So if you have these shapes, because basically you're putting shapes on a plane. Okay, you're putting shapes on a plane, and if you put these shapes on the plane that are perpendicular to your x-axis, then the volume is going to be with respect to your x. So whatever function you have, you solve it for y, so it's with respect to x. And then if it's taken perpendicular to your y-axis, the opposite is true. So you solve it for x. So it'd be x equals, and that's the function you would use with y as your independent variable. Alright, so we have the volume of the solid. So if you look at the right, I put that on there so you can see what the solid would look like. Yeah, so it's basically like a pyramid, but with one side it gets lower and lower and lower until it comes to a point. Right, the base of the solid region, it's going to be bounded by those lines. So if I sketch these lines really quickly, so here's our graph. That's like my y-axis. Here's my x-axis. And then if I sketch these, you would have f of x. Oops, it goes to, let's see, from 1, 2, 1, 1. So this is f of x, so it's 1 minus x over 2. And then this one is g of x, so it's negative 1 minus x over 2, or if you would distribute that negative in, negative 1 plus x over 2, like you see above. Okay, so these were what the base looks like. So that's this part here. Now we're stacking on top of the base an infinite amount of equilateral triangles. So this red part represents one of those. So you're looking down from the top, from like a helicopter view, and that represents one of those triangles. And then we set more on, and you notice the base of these triangles, as it gets further and further to the right, the base of these triangles gets shorter and shorter. So it's defined by something. Look at one of these from the front. So this is one of those cross sections of the, that's not exactly same angle, but this is your base. We need to figure out the area of one of these triangles. So go ahead and go back to trig and try to find the area of one of these triangles, and then when you want to check your answer, come back here and see how you did. So first of all, you need to figure out what the height is, okay, where you know that this well, the distance from here to there is going to be 1 minus x over 2, then minus the lower one, the distance from there to there. So it's the upper minus the lower. So upper minus, then your lower was negative 1 plus x over 2. And so when you simplify that, whoops, let's write that as the base. And then when you simplify the base, you end up with, what is it, 2 minus x. Alright, so that's total distance is 2 minus x. So the distance from here to there, oops, is 2 minus x over 2. And with an equilateral triangle, so if this is x, this would be radical 3x. So it's going to be this. It's going to be, let me pull this out here, it's going to be radical 3 times, you would have 2 minus x over 2. And so your area is going to be 1/2 the base, which is 2 minus x over 2. 1/2 the base is 2 minus x over 2 times the height, so that would be your square root of 3 times. And you can rewrite this as square root of 3 over 4 times just 2 minus x. That's the area. Now once we find the area, now we do the volume. That's when you would set up your interval. Oops, the area is pi. My bad. Pi times, yeah, radius squared. So that's squared. Okay, because the radius is 2 minus x. That's that distance from this line to that line. Alright, so then it's going to be pi, and then you're going to go from, in this case, 0 to 2 on your x-axis, from 0 to 2. And radical 3 over 4 times the radius squared, so that was 2 minus x quantity squared, with respect to x. Now you can use u substitution. I'm going to bring this radical 3 over 4 out. when you use U substitution, you end up with, hold on, oh, there we go. When you use U substitution, you end up with the volume as just negative quantity of 2 minus x. You have that to the third all over 3. So you can use substitution if you don't believe me, and then that would go from 0 to 2. The bottom does matter in this case. When you plug the top in, you end up with 0. Then you'd have 0 minus, when you plug the bottom, you'd have 2 minus 0, that's 2, 2 to the third is 8. So you have 8 thirds. But it'd be plus, because it's minus and negative, I guess. So it'd be plus 8 thirds. And then when you put this all together, you end up with radical 3 over 4 pi times 8 thirds. These will simplify down. That simplifies to a 2, that to a 1. So you'd have 2 radical 3 over 3 times pi. Wait a minute, why did I throw that pi in there? Hold on. Sorry. These are not circles. I'm used to circles. I don't know why I threw that pi in. So there's no pi. The rest of it I think is right. The rest of it looks okay. But there's no pi, my bad. You all probably caught that. This is a triangle, not a circle. And then we're going to label this as units cubed. And that's our answer. So two ways to find the volume. One is, the washer or disk method. That's when you use pi. And then the other method depends on the area that they are having you put on top. You're setting these shapes on top of a plane. In this case, they were equilateral triangles, so whatever this distance across was, the height up to the top and down the side also had to be. Sometimes they're circles, sometimes they're right triangles, sometimes they're squares, whatever. You just have to be familiar with how to do this and just be familiar with all of the shapes. The triangles are probably one of the more difficult ones because you're having to find the height and all that. But anyway, that's all for this section. Go ahead and try your notes, and in class let me know if you have any questions.